Thank you. So now we have Hiroka Aoki from the Japan Meteorological Agency, and they'll be presenting the effectiveness of the super-hydrophobic radome coating.
Hello, everyone. I'm glad to be here today. I'm Hiroka Aoki from Japan Meteorological Agency. So today I'm going to have presentation about super-hydrophobic radome coating. So we have newly started to using super-hydrophobic radome coating this year. So in this presentation, I will show you some characteristics of this coating and some observation examples. These are contents of my presentation. First, I'm going to talk about radome water repellency as background. And next, I introduce superhydrophobic radome coating we start using from this year. And then I'll show you some observation example by JMA radar with this superhydrophobic coating. So finally, summary of my presentation. In this slide, I will show you radomes we use. JMA operates 20 nationwide radars and 9 terminal Doppler weather radar, TDWR. Here are some examples. As you see, they are spherical radomes and nationwide radars, here 3, use radomes with a diameter of about 7 meters, and PDWR use ones with a diameter of about 11 meters. So, and radome surface is made of fiber reinforced plastic, FRP. So this slide, I'm going to show some issues related to radome water repellency. So as you know, when it rains heavily directly above the radar site, a film of water forms on the radome surface, and this water film attenuates radio waves, so it leads to underestimation of precipitation intensity. Here I quoted Curie and Hoskonen reported the amount of attenuation due to wet radomes. This graph, the horizontal axis is precipitation intensity, and the vertical axis is transmission loss and one-way loss. The line shows the theoretical calculations, and the points are result of scaled measurement. So about 3 decibels two-way transmission loss of radome at rain intensity of 15.1 millimeter per hour. So this slide is also about attenuation by wet radome. So levels of attenuation differs depending on the polarization. Vertical polarization is more attenuated because water flows downwards the surface of the radome. So this appears as ZDR positive bias. So ZDR is used for hydrometeor classification. So bias of ZDR lead to misidentification of precipitation particle shapes. So in WMO guidelines call for a difference of under 0.2 decibels between polarizations. Here, Dr. Frech reported significant bias in ZDR as a function of rain rate. Here is a case study reported in his paper. So upper figure shows ZDR, middle figure shows reflectivity for horizontal and vertical polarization, and the bottom figure shows ombrometer observation at radar site. We can notice ZDR positive bias when precipitation area reaches the radar site. The bias can be as high as 0.8 dB or more. And he mentioned that stronger vertical intensity attenuation can be attributed to the more or less vertical aligned water runoff from the radome. So in this slide, I will show you example of rain-related ZDR biases. This is an example of JMA radar, so Sendai radar. ZDR bias appeared when it was raining heavily directly above the radar site. In this example, a rain gauge near the radar site recorded 6.5 millimeter of rainfall in 10 minutes. The middle figure shows the precipitation intensity, radar composition. A strong echo was passing above the site. In this movie, images every 5 minutes are displayed for 1 hour. And this right figure is GDR observed by Sendai radar. GDR has changed to a larger value shown in yellow color. The area shown in green with a value of about 0.5 to 1.0 decibels changes suddenly to yellow color, about 1.5 to 2 decibels. It is thought that the ZDR bias is caused by wetting from heavy rain. This is another example for Murotomisaki radars. So same as the previous example, rain gauge near the radar site recorded 6.5 millimeters of rainfall in 10 minutes. So changes in ZDR can be seen when strong echoes pass through. And this is not the main point of this presentation. I would like to add some information, explanation about the ZDR displayed here. These data are pre-correction for attenuation due to rain echoes. So that means negative ZDR is seen behind the rain area, but here. The light blue or blue part can be seen. It has a value of about minus 1.5 dB to minus 4.0 dB. This negative ZDR is due to the flat shape of the water drop. So this is also the same example of Murotomisaki radar, but this is a graph shows the time series of ZDR. Data is as of August 2, 2023. So firstly, I will explain the data that makes up this graph. This graph is designed as a monitoring tool for ZDR bias. Ota et al. Reported at second WXR Carmon in 2019. To monitor ZDR bias, it is targeting weak precipitation. So from low elevation angle observations, we extract data that meets all these criteria. This table. So these criterions, symbol S represents the variation in data within certain area. So it is calculated as the median absolute deviation for data within 2 kilometer square around the target bin. The larger the S is, the greater the deviation variation. So then extracted data are averaged and displayed as the time series data every 5 minutes. So, and the blue dots is the data of long pulse region, and red is short pulse region. So data for individual regions are analyzed separately. So JMS dual-pole SSPA radar uses long pulse and short pulse observation. So radar cannot receive weather signals when it is transmitting. So long pulse transmission causes blind zone in the radar vicinity. So short pulse observation is needed to cover these blind zones. So up to this, I have explained how this graph drawn. So now let's take a look at the characteristic of the graph. So in this example here, an upward spike of approximately 0.5 decibel is seen at around 7 p.m. when heavy rain passing directly above the radar site. And some spike-like rises also appears. So these are apparent positive CDR bias due to wetting. And then there are other issues about radome surface, so, such as snow accretion. So this is especially noticeable on radars on high mountains in northern Japan. So when snow or ice accumulates radome surface, so radio wave attenuation may occur. As shown in these pictures, in 2004, Hakodate radar is in Hokkaido, so experienced very heavy snowfall and affected observations. Then let me introduce an example different from water film or snow. At Ishigakijima radar, as shown in these pictures, a greenish residue appears on the radome surface. This may be aerial algae or lichen. So Ishigakijima radar is in lower latitude region, so with a warm environment, and it is located on the top of a mountain on remote island. So that means it's surrounded by sea and vegetation. So these locations seem to be favorable for aerial algae or lichen. So such kind of residue may lead to decrease in water repellency of radome. So regular cleaning is required as shown in these pictures. So, but they are firmly attached and it is not easy to remove them. And so far, I introduced several topics related to radome water repellency. And here I summarize the requirement for radome coating. So first of all, it's essential radio wave transparency. So JMA's radar specification states that radome horizontal and vertical polarization should average 90% or more, and that the difference between the two should be under 0.1 dB. And water repellency, which is enough to suppress the effect of wetting or snow accretion and other influences. And weather resistance, ultraviolet rate, and other influences. So no need for recoating beyond the radar service life of around 15 years. So as part of regular maintenance, radomes may be cleaned every 7 to 8 years. And algae resistance. This is such as Ishigaki-jima radars. This reduces the need for cleaning at specific radar site. So JMA has adopted Sky Halo Has from 2023 this year as a radome coating that satisfies our requirements. So Sky Halo Has is a super hydrophobic coating developed by Subaru Corporation and Nihon Tokushu Toryo. These are Japanese companies. So here features of this coating. First of all, it is super hydrophobic. It produces a water contact angle of at least 150 degrees and highly durable. So the hardest super hydrophobic coating available. So it is hard enough to be used for aircraft. And also it is resistant to ultraviolet rays. Although there is no actual data on how long it will last when coated on radomes, but it is expected to have a longer service life due to these characteristics. And it is possible to recoat after many years of use, so it means repairability. And this coating can be used with an anti-algae agent. So mixing the anti-algae agent with coating solutions before painting. So it has also been confirmed that radio wave attenuation due to coating is negligible. We used this super hydrophobic radome coating on the Okinawa radar equipment. Okinawa radar was updated in April of this year. In that timing, we used new radome coatings. The radome panels are coated at the manufacturing factory, and the coated panels are carefully packed and transported to the radar site. And assembling the panels at the radar site is a photograph. And after installation, a simple check for water repellency was conducted. So I will show you observation data with super hydrophobic radome coating. This is an observation example of Okinawa radar. In this example, a rain gauge near the radar site recorded 10 millimeter of rainfall in 10 minutes. A strong echo was passing above the site. The right figure shows ZDR. So as you can see, no positive ZDR bias was observed even when heavy rain passing directly above the radar site. Although here only 1 hour is shown here, but no positive bias was observed throughout this rain event. This is an example of Matsue radar. It was updated in June this year and was also with super hydrophobic radome coating. Like Okinawa radars, no positive ZDR bias is observed in association with heavy rain. So it is thought to have effect of super hydrophobic radome coating. So then I will show comparison of regular and super hydrophobic radome coating. This graph on the left is shown in the same as previous slide. Example of Muroto Misaki radar, the time series of ZDR. As shown before, we see apparent positive bias due to wetting. And the one on the right is Okinawa radar with super-hydrophobic radome coating. In this graph, DDR remains almost constant. No major change on ZDR are observed despite heavy rain and strong wind throughout the day. So probably attributable to the super-hydrophobic radome coating. In this presentation, I showed only a few examples with super-hydrophobic coating observation, but even after checking many other cases, so no major effect changes of ZDR has been observed so far. Last summary of my presentation. Wet radome surfaces cause ZDR bias due to radio wave attenuation. The coverage with snow and other matter such as dirt, lichen, etc. also affects observation. Super-hydrophobic coating applied to updated radome equipment in 2003, so 2023. So for now, two radars with this coating, it eliminated ZDR bias even in heavy rain. From observation results so far, it appears to be effective. The effectiveness will continue to be monitored for reference in future JMA radar updates. That's all for my presentation. Thank you for your attention.
Do I have to disassemble the radome and put the coating on? And I put the coating on the whole radome. You understand? Yeah. If I want to apply this coating on my radome, do I have to take the radome apart? Put coating on one sheet and then up again? How do you do it?
You don't have to disassembling, just as the spherical shapes. So maybe you can sanding the now old radome coatings and coating this super-hydrophobic coating. So you don't have to reassembling. So
and one more question.
Yeah.
Is there less snow in top? Have you noticed less snow sticking from the radome coating?
But
Have you seen less snow with coating? Is the coating making the radome slippery so snow falls down?
Yes, this coating is effective for very low temperatures snow. So it means in the very low temperatures, snows perform as a solid state. So this radome has a high, very low friction, so it's very effective. But in the temperature near the 0 degrees, so such melting snow, it may stuck on this surface, maybe. So this effect is depending on the environment of the radar site.